So far, we've looked at the geometric way to arrive at the resultant. We would organize our vectors tip to tail, and we could find a resultant using the triangle law of addition or the parallelogram method. But unfortunately, that method won't always work. We've started to use a little bit of trigonometry, but we are going to be focusing today on using trigonometry to find both the magnitude of the resultant vectors, but also the direction of those resultant vectors. A third method we're going to be talking about today is component form. If you look at these two diagrams here, in the first diagram I have my resultant vector, or a vector r, and I can see the angle that it makes with the horizontal. If you look at the second diagram, it is broken up into its components. So a vector can be resolved into two perpendicular vectors whose sum is a given vector, or the resultant. When we have vertical and horizontal forces acting on an object, we refer to them as the rectangular components of the force. What I've done in this next diagram is I've placed my resultant vector on a Cartesian plane. And what I have here are two vectors, vector A and vector B, whose sum is the resultant r. Now I can see that vector A and B are my horizontal and vertical components. Together they make my angle theta and a right angle here. If I really think about what's happening here, I have my resultant vector starting at 0, and it's ending at some point which I'll just call P. I know that that can be written as xy. I know that the x is really just how far this vector A is. So the magnitude of vector A is equal to x, and the same thing goes for b. So if I wanted to travel to this high point P here, I need to go up some amount b. So the magnitude of vector b is equal to y. In order for me to figure out this point P, or my x and y, I need to use my primary trig ratios. I have a right triangle, I have some values, it should be fairly easy. So when I look at this, if I have cos of theta, we all remember that that is equal to adjacent over hypotenuse. So that is the magnitude of that vector A over the magnitude of that vector r. Now what I can do is I can rearrange this formula to get a by itself, or in this case just my x value. And I can do the exact same thing with sine. So sine of theta we know is opposite over hypotenuse. So the magnitude of vector b divided by the magnitude of my resultant, or vector r. Alright, sorry, I just had to make things a little bit smaller there. So I'm going to go ahead and I'm going to rearrange these like I was saying earlier. I can now say that the magnitude of vector A is equal to the magnitude of r cos theta. Now, we said above that the magnitude of A is just equal to x. So really, I could say that x is equal to the magnitude of r cos theta. I can do the exact same thing for sine. So I would have the magnitude of b is equal to the magnitude of r sine theta. And then again, in this blue star up here, I said that the magnitude of b is equal to y. So y is equal to the magnitude of r sine theta. So after all of that, I am just able to say that my resultant r broken up into components is equal to the magnitude of r cos theta, comma, the magnitude of r sine theta. And all I did there was plug in my x and my y that I solved for there above. If you look at this diagram, you will notice a whole bunch of vectors. They're all parallel to each other, and they're all going in the exact same direction. Now, each of these vectors are following the exact same path, so they are moving, they're the resultant of a vector that would be going horizontally 3 and vertically 2. Now, the Cartesian vector 3, 2, notice the square brackets here. Those are important. We're always going to be using square brackets for our Cartesian vectors. It would begin at point 0, or the origin, and it would end at point P, 3, 2. So what we've created right here would be vector OP, which is equal to 3, 2. And what this is actually also called, can't write here, is a position vector. All of the blue vectors that you see on my screen here can be shifted or slid or translated to the origin, and they would be directly on top of that position vector. If you think back to the previous slide, what we can now see is that when I write this vector like this Cartesian vector, I am breaking it up into my horizontal and vertical components. So here I would have a horizontal component of 3 and a vertical component of 2 to get my resultant vector or my position vector. In our first example, we're told that we have line segment RS that has the coordinates R, 3, 1, and S, -2, 5. So I've just done a quick sketch here. I've plotted those points. One thing I did want to mention is that when I drew this vector, the arrow is at the S because the line segment is RS. So starts at R, ends at S. Now when I look at this diagram, if I want to break this up into components, I have vector RS is equal to, now remember, square brackets because I'm breaking it up into components. I have to travel, so starting at R, I have to travel 5 units to the left and 4 units up. And so if I'm putting that into components, that means that I'm going to have a -5 for my X and a 4 for my Y. Sorry, I had to change that coloring there. It was bothering me. So for part B, it says determine the magnitude of vector RS. So now we're seeing magnitude. Remember, we have to include these bars here. So the magnitude of RS is equal to, since this is a right triangle, I am able to use Pythagorean theorem. I have this distance as 5 and this distance as 4. So the magnitude of RS is equal to the square root of -5 squared plus 4 squared, which is equal to the square root of 25 plus 16, which is equal to the square root of 41. To end off this note, I just want to talk to you about one final definition. So if you have a vector with a given head and tail, A is 1 point, so x1, y1, and B would be the other, x2, y2. The components of vector AB are found by subtracting the coordinates of its tail A from the tip B. So vector AB in components can be written as x2 minus x1, y2 minus y1. Now it only makes sense that if we were attempting to find the magnitude of AB, we would use our length or distance formula, which is just a variation of Pythagorean theorem. So we would have x2 minus x1, oops, there we go, squared, so that's my x component squared, plus my y component squared, so y2 minus y1 squared.